We are looking into induced polarization methods. These are the different units of measurement which we use in induced polarization method. First is the millivolt per volt. It is one of the common measurement of induced polarization method to measure the chargeability of the earth. Higher values of millivolts per volt indicates the earth is very much chargeable. That means the earth has got very high chargeability. So, it is the voltage the ground holds on when the current is removed compared to the voltage that the current was actively flowing. Right. What is induced polarization method? In induced polarization method, we had already seen the measurement of potential is measured after the stopping of application of the current. So, what is this unit? In this unit, what we are doing is we are trying to compare, we are comparing the voltage that was measured when the application of current was made and what is the voltage that was existing after the application of current. It is something like we are comparing the voltage which we have measured in the resistivity method. In resistivity method, what did we do? We measured the potential during the application of current. This is time and this is the potential. Right. So, in resistivity method, when the current is applied, the potential is measured. At this time, we have stopped the application of current, then the voltage completely diminishes, right. So, here in millivolts per volt, what we are trying to compare is this voltage with that of the voltage that we are measuring as and when we stop the application of current. Then the second is milliseconds. Second unit is known as milliseconds. It is used when measuring the ground's response to impulsive sources, right. That means we will use some impulsive sources. During that time, how much is the time until which ground is able to remain charged, right. Then in the third unit is known as percent, is used when we use multiple source signals, right. Suppose if you use the currents from multiple sources, then we measure the percentage. Milliradians are the unit which we often use to record the phase difference between the source and the received signal. We are going to see all of them little later. Right? These are the units of measurements in induced polarization method. Now, coming to the actual measurements in the field, the measurements can be made in two different methods. One is known as time domain and the other one is known as frequency domain method. Right. In time domain induced polarization method, which is also called as or abbreviated as TDIP. Right. What we are measuring is we are trying to measure the transient decay of voltage. Right. In other words, our focus is over this area, right. This is the voltage which we are measuring when we are applying the current. At this time, we have stopped the application of current, right. Hope you can see where I am marking, right. That is this area. At this time, we have stopped the application of current. So, until this time, it is actually a simple electrical resistivity method. This is what we did under resistivity method. Now, we stopped the application of current here. Now, our focus is going to be on this area. This is what is known as IP method, right. So, we are going to measure the transient decay of voltage, right. So, here this time domain method often used in groundwater investigations. Mostly groundwater investigations are carried out by time domain induced polarization method, right. So, what we are measuring here is the chargeability M. Chargeability M is nothing but the red area, that is what we are focusing on, right. It is a referred as M letter, capital letter M, which is essentially we try to estimate the area under marked in red color here, right, which is given by this equation where chargeability is equivalent to 1 by Vm, that is the maximum which we are measuring, that is this one, with we are integrating for this one, which means we are trying to understand how much is the area. We can take up any time, right, maybe this can be T2, this can be T1, or we can take the entire area, right, which in fact we are trying to understand what is the normalized area between two different times. That is what we call it as chargeability, right. So, in time domain IP method, which is often used in groundwater investigation, we measure capital M. In the second method, which is known as frequency domain induced polarization method, which is FDIP, here normally we use alternating current, unlike the battery which we use for the previous one time domain. Here we use alternating current. Why do we need alternating current? Is we need to apply current in different frequencies. Normally we are injecting two different currents, right, at that means two currents at different frequencies, and we measure the apparent resistivity for both of them, right. So, normally it is a normal practice to apply current in 0.1 hertz and 10 hertz. We can use other hertz too, right. It is generally we apply current in two different frequencies, right. The convention mostly we adopt 0.1 and 10. This is what is known as time. This is the major difference between the time domain and the frequency domain. In time domain, we just applied current in one frequency. Our focus was on the area after the stopping of current. We are trying to estimate the normalized area that was shown in red color in the previous slide. Whereas here we are trying to understand the difference between the applied current in two different frequencies, right. We are applying current in two different frequencies and we measure the apparent resistivity. And here too one advanced method which is known as spectral induced polarization method. Here rather than applying current just in two frequencies, we apply current in different frequencies ranging from 0.1 to 1000 hertz, right. This is how frequency domain is different from that of the time domain method, right. So, this is done basically to understand how the earth responds to different frequencies of current, right. So, we are actually estimating the apparent resistivity for different frequencies of current that was applied, right. So, mainly this is used to locate portions of the earth where the resistivity decrease as the frequency of the applied current is increased. Here the usual unit of measurement is this, right. That means we try to understand the phase difference between the applied as well as the measured signal, which is explained further in this slide. So, here we are trying to understand what is known as percent frequency effect, which is known as PFE, which is given by this equation, right. That means what is the apparent resistivity which we had measured when we applied current in two different frequencies divided by what was the apparent resistivity which we got when we applied the current in the first frequency, right. So, this is what is known as percentage frequency effect, which is also alternatively given by this also, right, frequency effect instead of percentage, right. And the other unit which we can use can also be like we had seen milliradians. We can also use this unit here, right. What we are going to do is, what is the phase difference between the first applied current and measured voltage. Because we are applying current in different frequencies, we are able to have this result. As we see in this diagram, we will get this result. This is the applied current, measured potential. So, what is the difference between the two, right? That is what is known as radians. We can measure either this or the percent frequency effect. So, this is how induced polarization method is carried out either in time domain or in frequency domain. Now, coming to the interpretation of the data. Most of the interpretation is qualitative. In induced polarization method, either we get the map of a particular area, that means we try to get the map of, let us say, chargeability M, or we may also estimate the milliradians, or if you are using time domain, we are going to make use of what is known as chargeability. If you are going to make use of frequency domain, we can use phi value, and interpretation is done by looking at the how the values were varied over space. Suppose if you are using the electrical resistivity imaging system, then we are able to get the chargeability of the subsurface in a cross section, as you see in this diagram, right. So, we can qualitatively interpret and identify the region which is very much chargeable. This can be differentiated from the other area. In plan, this is a plan or map, or in a cross section, as you see here, we try to identify regions which were remained chargeable for more time, right, in terms of time too, right. So, this particular region was very much charged for a more amount of time, right, compared to the blue part, right. So, this is how we try to qualitatively carry out the interpretation. The other method of interpretation, as we have been seeing in the beginning, right, even in cell potential method or even in resistivity method, is the inversion, right. We can also carry on with the interpretation by IP inversion method. So, what is inversion method? In inversion method, we have got some data in the field, right. After our survey carried out at the site, we would have done maybe on a grid pattern. This is the plan. We would have had the IP values at different locations, right. Or if you had carried out along a profile, that means this is the cross section, beneath the surface you have the values at different locations. So, this is plan, you could have done like this, or cross section. Let us imagine we have done a work on in this manner, right. Now, we have the measurements at different locations below the surface, right. Now, check whether the values are correct, whether it needs to be corrected for some error, right. All that thing have to be done now. Now, the data is ready for interpretation. After that, as we had seen in the previous slide, we can directly interpret the data which we have. Whereas, in inversion, what we are going to do is, right, we will kind of generate a model, right, with a prior knowledge of the site, right. We need to have some prior knowledge about the site. That means, you are carrying out the survey on the surface, so you know whether it is a sedimentary formation or a weathered rock formation. Are you expecting a weathered rock up to certain depth? So, based on the field knowledge, you try to assume this is the likely subsurface configuration or subsurface geological situation for that site, right, and also come out with a criteria for misfit, right, and also come out with a objective function. That means your objective is to check whether your assumed model is existing there or not, right, have a objective function. So, the objective function can also be a kind of a misfit criteria, can be maybe like correlation coefficient or root mean square error, and your objective is to come out with the geological model of the subsurface, right. Now, perform inversion. What is inversion? We are assuming certain subsurface formations. This is layer 1, layer 2, layer 3. Layer 1 may be silt, layer 2 may be sand, layer 3 may be sand, consolidated sand, which is sandstone. We assume certain thicknesses for these layers, and in such a situation, if you carry out the investigation on the surface, what is the value which we will get can be theoretically computed. Okay, what is the induced polarization which we will get for this assumed formations of certain thickness, some true resistivity, right? Each formation we assign some resistivity, and then we will be able to come out with the results. Okay, that is what we are estimating the results, or we are calculating the results. Then we compare the results which we obtained by inversion. This is inversion and this is the field data. Okay. So, we compare the results which we have obtained by inversion with the field data. Are they matching? So, how do you decide whether they are matching? You have chosen some misfit criteria, maybe root mean square error or correlation coefficient. What is the correlation between this? This is the field data with the inversion data, right. So, when they are reasonably matching, then you go to the next stage. If they are not matching, you again iterate, right. How do you iterate? You change the configuration here, right. So, the thickness I am changing, or the material itself I am changing, and coming out with a new set of induced polarization values, right, maybe chargeability, capital letter M at different points. Then again I compare with the field derived data, right. So, I compare, and if I am satisfied, I go here. If I am not satisfied, I go and iterate. So, this is how I keep iterating till we come out with a stage where our field data is reasonably matching with the inversion data we have obtained by calculation. Suppose if both are matching well, what does it indicate? If both are matching well, then we generate a image from the assumed model. Okay? That means if both are reasonably, that is both field derived data matches with the model we have assumed for inversion, right. We compare these two always. If there is a mismatch, we go and iterate, and finally we got a one model which is nearly 90%, let us say 90% similar to the field. Okay. So, the model which we have got is almost 90%. As an example, I am giving you this number. So, you would have fixed up a misfit criteria, right. Imagine now I fixed up, if I get a match of nearly 90%, I am satisfied. Okay. So, now for 90% fit I could get for the assumed model, and now what is the inference? Whatever I have assumed for this model. So, for example, I would have assumed first layer is of 1 meter thickness, second layer is of 5 meter thickness, they are of certain resistivity, right. Maybe resistivity is given by letter rho. right? Resistivity of first layer rho 1, rho 2, rho 3. We have assumed and we have estimated or evaluated the IP data that we have compared with the field data. Now, we could get 90% match. So, what does it indicate? Whatever we have assumed here is existing at the field. So, this is what is known as inversion. The concept of inversion is the same for all the geophysical methods, right. So, inversion is one of the technique which we often use in induced polarization method too. So, interpretation is made by qualitatively looking at the image or by inversion as we had seen now, right. Now, coming to the applications part, these are the broad applications mainly in groundwater investigations, obviously in mineral exploration, and also for understanding sulfate ores, because sulfates are having a capacity to remain polarized for longer time, right, and strength of the IP effect depends on the conductive mineralization and the pore fluids. We had seen some process already. Why do we have induced polarization, right? Because of the interaction between the mineral and the fluid around that, right. And massive sulfates, as I told you, produce strong induced polarization. So, often induced polarization method is used in mineral exploration and also in groundwater investigations, right. Now, let us see how maybe this is of interest to a mining engineer or a geologist, right, how induced polarization can help us in delineating ore bodies. So, here you can see, right, there is a ore of silver beneath the surface of the earth, and they have carried out both the resistivity method as well as IP method. So, this is IP, the dotted line is the resistivity. In both the method, we could get a different signal, especially in the case of IP, chargeability was very high in this zone, right, this zone. When chargeability is very high, certainly it indicates a metalliferous deposit, right. So, in this case it happens to be a copper and silver ore body. So, this is how we have delineated the presence of ore body by induced polarization method. Please remember, since the resistivity meter which we are using, right, for cell potential method or resistivity method, the same meter can be used for IP method also. So, usually when we carry on with the geophysical investigation by electrical method, we will conduct all the three methods. What are all the three methods? Resistivity, cell potential and IP method. So, that is why here they have conducted resistivity method too. Resistivity was also equally low in this zone, right. So, this is how induced polarization method help in delineation of mineral deposits, which is of an interest to a mining engineer or a geologist, exploration geologist. Now, in another case study carried out by this scientist, right, they had tried to deploy both resistivity method as well as induced polarization method. What they have done, focus your attention to the diagram here which is sourced from this site. They had carried out vertical electrical sounding as well as induced polarization method at all these sites, right. So, especially this is site 1, 2, 3. These are the three sites which has been used for interpretation. Obviously, it is a as you can see here, resistivity method is unable to give much of an information at this site, because the formation below, they are all derived from the work of river. So, they are all alluvial deposits. So, alluvial deposits are poorly differentiated by their resistivities, which means resistivity method, that is the vertical electrical sounding they had carried out, could not give sufficient information, right. What is vertical electrical sounding? In vertical electrical sounding, over this point, we will spread the electrodes either side symmetrically, slowly we will move. So, we will end up in having a data of depth versus apparent resistivity, so that we will know the resistivity of the subsurface at different locations, as I am drawing, please notice, right. However, it was not giving sufficient information, right. This is the location number 1. This first one shows the location number 1. So, here is location 1. Here what you see is the light colored line is the resistivity variation. So, there is not much of a variation in resistivity with respect to depth. So, what is this axis? This axis is the electrode spacing, right. They have used Schlumberger method. So, AB by 2 refers to depth. So, this is the depth and this is the apparent resistivity, right, apparent resistivity. So, there is not much of a variation in apparent resistivity, more or less it is horizontal, varying between maybe 30 to 40 or 50 ohm meter, right. So, it didn't give sufficient information. The same for location 2. This is location 2. In location 2 also, this is the resistivity curve, not much of a variation. The same is applicable for location 3, that is, this is location 3, right. So, here too the resistivity did not vary very much. Okay. However, IP method is able to clearly distinguish, we are able to clearly distinguish 3 different formations below this surface, right, based on their chargeability or polarization, right. Let us have a look into how we are able to distinguish. Let us take in all the 3 cases, 1, 2, 3, here is the chargeability. The axis of chargeability is shown here, right, on the right hand side. Right. Chargeability is given in terms of percent eta, right. And you can have a look at with respect to depth how the chargeability increased, whereas at location 1 resistivity was more or less horizontal, whereas chargeability, I will use dotted line, it varied like this. In the second location also chargeability increased and then decreased. In the third one very much, that is this side, right. So, it increased and then decreased. What is very clear from these 3 diagrams is resistivity did not vary very much, however, chargeability varied very much, or in other words, IP effect varied very much. So, based on this we could decipher, right, the first part of this curve is one layer, second part is the second layer, then the last part wherever there is a major change in the slope, break in the slope of the curve, indicate the third part. From there we can derive. So, look at the third bullet point here, the top layer has got very less polarization, right. Top layer is of weak polarizability, right. The thickness approximately is about 2.2 to 4 meters, right. The chargeability is about 0.8 to 1.5, right. Chargeability is given in terms of percent, right. How are we explaining that in terms of percentage? That means when the current is flowing, when you are applying current, what was the voltage which you have measured. When you stop the current, what is the voltage which you have measured? What is the percentage difference? That is what is shown here, given here, right? This is for site 1. Sorry, this is for layer 1. So, at layer 1, that is the first part, the chargeability varied only between 1 to about the chargeability varied between 0.8 to 1.5%, right. Here this axis gives us the percentage value, right. So, in layer 1, if you see, this is the first layer, right, it varied only up to about 2 or so. How about here? Here also it varied only up to maybe up to 2. Here little bit more, but on an average we say it is the chargeability varied from 0.8 to 1.5. The corresponding thickness is about 2 to 4 meters. So, that has been interpreted as a loamy layer, which is also dry. That means it does not have any saturation. It is a dry loamy layer. Then the interpretation of the second layer. Second layer is strongly polarizable. We can see in all the 3 diagrams, 1, 2, 3, that is this part. At all the 3 locations, right, we have measured very high chargeability at the second layer, that is this layer. So, the thickness of the second layer is expected to be about 18 to 20 meters, right, and the chargeability is little bit higher. Previously, it was only up to 1.5, here it is about 5%. So, this has been delineated as a clayey sand layer, right, clayey sand with fresh water, that has led to high chargeability. So, it was deciphered as a clayey sandy layer. Then the third layer. The third layer is comparatively of higher thickness, right, and the chargeability is very less for the third layer. Chargeability is very less for the third layer. Hence, the third layer is interpreted as a impervious rock. Impervious, in this case it is a siltstone. So, there is no water at all. So, chargeability is very less. Thus, in the study carried out by this group of people, right, we could clearly differentiate the application of electrical resistivity method and the induced polarization method. In this site, as claimed by these scientists, which is available at this location, right, it is evident that resistivity did not give much of an information, right. That means, resistivity method did not give sufficient information, whereas at the same site we could get sufficient information about the subsurface by induced polarization method, right, because resistivity was more or less the same. Why resistivity is the same? Resistivity for the 3 different formation, that is dry loam as well as clayey sand and siltstone. It is not of greater variation. There is some marginal variation here, but the variation is not significant. So, I am erasing. You can see now, see the light colored line is the vertical electrical sounding, not much of a variation, whereas IP showed lot of variation, that is the dark, that is this line, lot of variation we could get in the IP. Further, using IP method, we are able to differentiate the rock types also based on the level of saturation. Then in the next study, these people has successfully deployed induced polarization method to understand groundwater contamination, right. Here on the right hand side is a map showing us the variation in the induced polarization, right. So, they had carried out induced polarization survey at different locations. This is a map of a region, right? They have carried out induced polarization at different locations of this particular area, right? After having completed the work, what they have done is, at different locations I have the value of, let us say, chargeability, right. Here they have used the same chargeability which we had seen previously, that is given as eta A in terms of percent, that is percent chargeability was estimated at different locations. Then what we have done, we have interpolated the values which we have got over the entire area. Over the entire area was interpolated, and then we had estimated for the entire area they had carried out the survey. That means here is the first station, second station, third, fourth, fifth and so on, for which they had carried out the interpretation. How the interpretation was done? Interpolation was done between the points, and then lines of equal chargeability has been prepared. So, this is a map of iso chargeability, right. Iso chargeability has been made, that means iso percent chargeability map has been prepared. Please focus your attention to this map, right. Here is a region where the chargeability is around 2, yeah, I can read it as 2. Here is 1.5 contour, here is 1 contour, this is 0.75. So, here is the 2, 1.5, right. Then this is 1, this is 0.75, okay. Now, we could decipher different areas. So, the one which is having the largest IP anomaly, that is with a percentage of around 2.5, right, that is very close to this, right, that is this area, very high chargeability, right. Similarly, here I am just coloring it in red now. So, this region is near A, which this particular region has got very high IP anomaly. That means this region is very close to the location of contamination. Probably these are the locations of contamination, right. Then the next hatched line, hatched part, that is this part, represents chargeability of 1.5, right, about 1.5. So, this is above 2, this is above 1.5, right, this is over 1.5. This also represents the next maximum zone of contamination. This is the highest next level, right. Then the region beyond 1.5 with a polarizability less than 1 or 0.75, that is the rest of the area marked in white color, right. This region was interpreted as the region free from contamination, okay. So, this is how induced polarization method has been successfully deployed to understand the level of groundwater contamination in a particular area, right. So, this case study helped us to understand how induced polarization values will vary due to contamination. When the groundwater is contaminated, the earth is able to remain chargeable or able to very easily get polarized, right. Polarizability gets increased due to groundwater contamination. That is what has been indicated by this case study. So, we have seen how induced polarization method can be carried out in these two lectures. right? How this is different from that of resistivity method? Can you tell me how it is different from that of resistivity method? How it is different? So, in resistivity method also we had used 4 electrode. I am drawing the Venner configuration now. In resistivity method, the electrical potential was measured while applying the current, right, from the battery. While applying the current, we measured the electrical potential, using which we estimated what is known as apparent resistivity. In IP method, what we are going to do? We are going to use the same arrangement. Only difference is the electrical potential will be measured after stopping the application of current. Stopping the current. That is, this is resistivity method, this is IP method. That is the only difference. So, we have seen what is the difference between that, between the IP method and that of the resistivity method, and then we had also looked into the theory behind induced polarization, right? How the earth is provoked by the application of current, why the earth is provoked, or why earth is made to remain charged, because of the fluid that is present in the earth. Mostly it is groundwater, water and the solids and the mineral grains. If you have clay, clay performs in certain way. If it is a metallic grain, it is completely getting polarized when you apply current. That itself becomes a small particle, becomes positively charged and negatively charged on the other side. When you remove the application of current, it takes some time for the ions to realign, reposition themselves. Until that time, the earth remains charged. That is what we are making use of in IP method. There are 2 ways in which the survey can be carried out. Before that, please remember, induced polarization method can be carried out in any electrode configuration, in all the electrode configurations which we had seen in resistivity method, which are like Venner method, Schlumberger method, pole-dipole, dipole-dipole method and so on, right. And the way in which the survey can be carried out for induced polarization method is of 2 types. One is we can focus our attention on the red area, that is time domain. Normalized area we are measuring, that is known as time domain IP method. Then we had also seen frequency domain IP method. In frequency domain, we use 2 different currents or multiple frequency currents, right, to estimate the phase difference between the applied and the measured signal. Then toward the end, we had seen what are all the applications, and we had seen some case studies of applications of induced polarization method. Thank you.